So we're going into lesson 7.6, talking about function notation. And this is going to be just basic equation work, but instead of things with x and y, we're going to start to introduce a different notation using f of x. And if you look at the big idea, when a function f contains this ordered pair x and y, so we've got that ordered pair, it's being used in an equation, then y is the value of the function at x because y equals this. So based on x, the independent variable, whatever we plug in creates y, so y is dependent on x. So y is the value of the function at x. Given x creates y, we can write y equals f of x. So we're going to be talking about function notation. We're going to be talking about rewriting these using f of x instead of y. And this is basically just the function of x. So for function notation, looks like this. And you would read it. We'll put this in quotes so you know. F of x. That's how you're going to read this. So we're going to be rewriting these. Instead of y, we're going to write this. And you're going to read it f of x. And let's make sure we know what it means. It means that a function is given in terms of x. So that just seems a little confusing here at first. So let's jump right in and apply it so you can understand it. So example number 1, we're going to rewrite each of the following in function notation. So basically, y is dependent on whatever we plug in for x. Y is the value of the function at x. And so this function is completely based on x. It's in terms of x. And so to rewrite this in function notation, basically everything is based on this. And so f of x, or the function of x, is 5x plus 7. So at first you're like, okay, all I did was change y to f of x. And for right now, yes, that's basically all you need to know. So here, y is equal to 400 times 0.5 raised to the x. Okay, y is completely based on x. Y is the value of the function at x. And so we can change this and say the function of x is 400 times 0.5 raised to the x. So at this point, all we're doing is changing y into function notation, and the function is based off of x in this case. Now, you can use other variables, and so then this would change. So as we come over here, we're no longer using x and y. Okay, so a is the dependent variable. Everything is dependent on this t. Whatever you plug in for t, it's going to create a. So this function is based on t. So it's the function of t. It equals 2500, 1.075 raised to the t. So if you notice, whatever variable is being used in the equation that you're actually plugging into to solve, that's what the function is based off of. So we write the function of that. So it's kind of like this dependent variable disappears and you put it into function notation. Now, there's another way to write this. If we want to be a little more specific and not as general, we can always use f of x, function of. But if you want to be more specific to the variables that we're using here, you can say a of t equals 2500 times 1.075 raised to the t. And I think that one will make a little more sense for you guys. So technically over here you could put y of t, but to be honest, anytime we're using x and y, we're pretty much always going to say f of x. But if we're using some other variables that represent something more specific in a given situation, it's nice to use that variable here so we can better and fully understand what's going on. So over here, we could change this to f of, e. Okay, this function is based off of e. The value of the function comes from e. And so it's 9.5 minus 8.75. E, it's the function at e. Or, okay, we've got the variable d. So d of e equals 9.5 minus 8.75e. So notice the right side never changes. We're just basically changing the left side into function notation. Now at first you're like, well, that just seems pointless. Why am I doing all that? Okay, so we're going to slide down to example number 2. So given a function with this equation, f of x equals 5x minus 9, find the value of. So this is the function at 2, f of 2. And so f of x is 5x minus 9. So f of 2, so we're going to start with 5x minus 9, is 5 times 2. So when you see the notation like this, we want to know what's the value of the function at 2. So we're plugging in 2 for x. F of x, so there's your x, f of 2. So here's x, we're plugging in 2. So 5 times 2 is 10, and 10 minus 1 is 9, and so f of 2 is 1. 10 minus 9 is 1. So the value of the function at 2 is 1. So what's f of negative 4? So again, we have 5x minus 9. F of x is 5x minus 9. So f of negative 4 is 5 times negative 4 minus 9, which is negative 20, negative 29. So I can write f of negative 4 equals negative 29. How about f of 0? We're still basing everything off of this original equation, or this function. So f of x equals 5x minus 9. F of 0 equals 5 times 0 minus 9. So it's 0 minus 9, negative 9. F of 0 is negative 9. All right, and now we can take it a step further. So now we're going to take the function of 3 plus the function of negative 7. So basically what you need to do is find the value of the function at 3. So plugging in 3 and get the answer. And then also find the value of the function at negative 7, plug it in and get the answer. And then you're going to add those two together. So let's start over here with this one. So 5x minus 9 is the function. And we're going to plug in 3. So it's 15 minus 9. That's 6. Now we also need to find f of 7. I'm sorry, negative 7. So we're starting with 5x minus 9, plugging in negative 7. So negative 35. That's negative 44. And so since we're adding the function of 3 plus the function of negative 7, all right, we're going to add those two together. So 6 plus negative 44, that's negative 38. And so f of 3 plus f of negative 7 equals negative 38. Okay, and I'd like you to write out your answers like that. I think it's very helpful to fully grasp what's going on here. Okay, so function notation is kind of just a new way to write things, and whatever letter is inside your parentheses here and becomes a number, that's what you're plugging in for. So if you flip this over, example number 3 says, consider the 3 equations on page 397 in your textbook. Okay, so we're going to grab that, and it's for the population of a town. Write each equation in function notation. So if we quickly look on page 397, we've got a graph here, and we've got 3 different equations representing 3 different lines. We've got this straight line here, p equals 100,000. We've got this straight line that's increasing, so p equals 100,000 plus 3,000x. So we know that's linear. And then we've got this curve that's exponential. So 100,000 times 1.02 raised to the x. So we have a 2% increase. And so we're going to write all of those in function notation. So let's start with the ones that we've got the way they were given to us. So the first one looked like this, and let's just start there. Now you could just change it to f of x equals this, right? But let's be more specific. So p as population, you could even use that. But what we're going to do is we're going to refer to this as our exponential function. And so we're going to use e to represent this equation. So e of x equals 100,000 times 1.02 raised to the x. So we're going to use an e to signify that this is exponential form. The next equation was 100,000 plus 3,000 x. So this is an mx plus b form, right? Here's your slope, here's your intercept. And so this is linear. So if I'm going to write this in function notation, I'm going to use an L of x to show that this is my linear function. And the last one just says p equals 100,000. And anytime you just have a letter equals, like y equals this, that creates a straight line on your graph. So this is a constant. Population never changes. Population is always this. So this represents population growing at an exponential rate, 2%. This shows population growing linear. Okay, it's going up 3,000 over and over and over. And this one never changes. It's a constant. So this represents your constant situation. I'm going to use a C to represent constant. And now we're going to plug in, and we're going to evaluate each one of these functions separately using 10 as our value. So let's start with e of 10. So for e of 10, we're going to go ahead and we're going to plug directly into this function. So 100,000 times 1.02. And now since e of x, here's my x. Well, 10 is sitting in that x spot, so 10 is what's going in for x. So I'm just plugging in 10 here. You can plug this in your calculator. And just kind of rounding it off a little bit, it's going to come out to this number. And so we're going to round it to a whole number. We're going to say it's approximately 121,899. So using our exponential model, plugging in 10, okay, we get this value. Now let's use our linear function, plugging in 10. So we're going to take that equation, or that function, and we're plugging in 10 right there. And so when we multiply here, we're going to get 30,000, and you're going to add it to the 100,000. So that comes out to 130,000. This one was 121,000. And then our very last one, c of x. So we're doing c of 10. Well, if you look, there is no x in this function. There's nowhere to plug it in. It doesn't matter how many years it's been. This is a constant 100,000. So there's literally no variable to plug into. And if you think about the reason for that, this represents a constant function or a constant equation. And we're in this one specifically talking about a population that never changes. So it doesn't matter if it's 10 years later, the population is still 100,000. Where if it's linear and going up 3,000 every year, after 10 years, it started at 100,000, now it's at 130,000. And in your exponential function, if the population is growing exponentially at 2%, after 10 years, we're at 121,899. So it's really just getting used to writing and reading these equations in function notation and as functions, which at first will be a little bit of an adjustment, but you kind of just get used to it, and it should be pretty simple moving forward.